All right, so welcome to Math 150 Multivariable Calculus. This is lecture 6, March 3rd. And what I want to talk about today is a question from the class about orbits of planets, to continue what we did before. Unfortunately, during the COVID restrictions, I cannot take people to the library to actually see the first edition of all the great books. We have first editions of Newton's Principia, Galileo, Copernicus. If people are interested next year, let me know. I'm happy to organize a trip. All right, but I thought we've seen a lot of standard limits and calculations like that. I thought we would do a little bit more interesting ones today. So first, let me talk a little bit about level sets. Even though level sets won't be on the first exam, they will be on later exams, and it is a good topic. All right, so here is a function, and I'm using commands in mathematical. Manipulate allows me to change parameters, and I can create little groups. I'm going to do a three-dimensional plot of two functions. The first function is h. So no matter what value of x and y you give me, I give you h. What kind of surface is this going to look like? The plane. How high above the xy axis will the plane be? H units. Oh, this is my level set of height, c. So I'm doing it h this time. The height. And I can just change the value of h and see where it intersects my plot, and that will give me the different level sets. So if you can experiment, it's always great. So then I get the sine of xy over xy. And we know the limit of sine of h over h, as h goes to 0, that goes to 1. So the function sine of h over h is going to be at most 1. It has a very nice behavior. Because it's xy over xy, it's going to be symmetric in x and y. And I'm going to plot as x and y go from negative 10c to positive 10c. So depending on the value of c, I can zoom in and zoom out. So here, I'm going to make c smaller, so I'm going to zoom in. Now I'm going to zoom out a little bit. If you look, you always want to check the axes. The axis is going from minus 0.2 to 0.2. Well, we know at 0, the function should be equal to 1. And that's why you have this cutoff over here, because Mathematica is having trouble showing everything together. So you always want to be careful when you have an image. Are you interpreting it correctly? Is it displaying the truth, or is there some kind of presentation issue? If I zoom in, I'm not going to have that problem. If I zoom in enough. And so here we go. I've zoomed in a tremendous amount. Let me zoom back out a little bit. Okay. So if I look over here now, I've got my height at 0.12, and you can see where I'm hitting my surface. And as I move the height, you can see it moving up. And when it gets to just a little bit above 1, there's no hits. If I make it 1, it will hit at exactly 1 point at the top, which you can't really see. If I make it 0.98, now you can see it's just a little bit below, and those intersections is going to be the level set. So I really like the ability to use Mathematica to see images like this very well and to explore the level set. And then again, as I move things, I will see different values. I can move the level set down a lot. And if I move it sufficiently far down to -1, I'm not going to see anything. All right, so this is looking at level sets. I want to now turn to questions about planetary motion. If I can find that. It was missing one window, and there was a window that said show all windows, and that was the one missing window. Gotta love it. All right, so here I have a parametric plot, cosine t sine t. That's going to just be a circle. So as t goes from 0 to 2 pi c, I'm going to just go around c times. And c, I can choose what it is, and it's just going to plot. So there is a particle moving in circular motion. So a lot of the ancient Greeks thought circular motion was beautiful. All things should be circular motion. Okay. Where should the circle for the planets be centered around? Or where did people think it was centered around? Some thought the sun, but a lot of people thought the motion was centered around the Earth, right? And now we know, that's foolish, it's the sun. but it's actually not the sun. The sun itself is moving, so we can be moving around the sun, which is moving around the Milky Way, which is moving around the local cluster. We'll ignore stuff like that for now. And so the question is, what can you do with circles? Imagine the only type of motion that's possible is circular. And I want to do a strange set of limits now. So what I'm going to do now is here's another kind of circle, cosine t sine t, but now I'm going to give it some height. And the height is t over 20. So if there wasn't that third component, it would just be a circle going around the xy plane. What happens now because of that t over 20? What happens as time passes? It's spiraling up or down? Up. And so I can change the speed of time by hitting these buttons. I can slow things down. I can speed things up. And you can see it spiral. And so it's still going to be, if you look straight down, it's going to be circular motion, but this is a great example of cylindrical coordinates. Continuing, let's come down to a little bit more complicated coming up. So first, the cosine t sine t, I'm just plotting a circle. And I'm going to plot two things. I'm going to plot that circle because I have my brace here. That means this brace here means start what I'm plotting, and the brace over here is end what I'm plotting. And this is going to be a pair of points. So this is the first function, which is just a circle. The next one, if r equals 0, it's just a circle again. It's the same circle. But now what I'm doing is on that circle, I'm drawing a circle of radius r. So if r equals 0, there's no movement. But if r is not 0, I'm going to move up a little bit. And then I'm going to move up, cosine ts, sine ts. If s equals 1, that circle is going to be moving at the same speed as the other circle. But by playing with s, I can change things. So I can hit play over here. And not surprisingly, when r equals 0, the two of them are perfectly aligned. Okay. I can now make r a little bit larger. And this is going to, that's just shifting things over, okay? Because I've fixed s to be 0. So because s is 0, cosine of ts, that's just cosine of 0, that's always going to just be 1. Sine of 0 is just going to be 0. So I'm going to just shift the circle a little bit to the right. That's not interesting. Let's make s positive now. Ooh, so you can start getting cool things. So let's make s equal to 0.5. Rational numbers will work out nicely. And now, let's see what happens. And now you can see a more interesting curve that it's going to pass around. And this is actually a much better choice than what I did in the first section. Because you can see, all of a sudden the planet is moving, and then it moves backwards, and then moves forward again. This is the retrograde motion of Mars. And if you choose these parameters correctly, you can actually come up with ways to describe the strange behavior using just circles on circles. What if circles on circles wasn't enough? What could you do? So I start off with a circle, and I have another circle on that circle spinning. What if that doesn't give me enough freedom? What could I do next? So I started with circle, then circle on circle, circle on circle on circle. And if that's not enough, circle on circle on circle on circle. And by putting enough of these, I can get almost any shape I want. Then the question becomes, well, how many circles do you need? This is elegant. Is there a better description of what's going on? By choosing different values, we can get lots of interesting behaviors. And so let me start. So I was going to say, if you remember the spiral graphs from, you can start to see some strange behaviors. And if we choose perfect integers, it's nice now, there's a little bit of a haziness, and a lot of that's your processing power. So be very careful about trying to extrapolate too much from what you're seeing, because I'm asking it to do a lot on a laptop that's getting old. And that's, maybe later we'll talk about how to do fractal drawing and the issues of how to compute things quickly. These are tremendously valuable issues. But when I give it a second to pause and catch up, then you can see things getting a little bit better. if I do 1.75, which is a really nice rational number, things are going to clean up much, much nicer. So there's a tremendous amount going on here. The main idea is just talking about this notion of limits. So you put limits, and before have been more like approaching a point. But this is a different type of limit, and this is done a lot more later in the semester. When instead of just approaching a point, we're going to be looking at summing various functions. It is amazing. This dust was not moved from the first section, but now somehow my computer's at a different zooming in. Okay. So, how many of you have seen these series expansions? E to the x is 1 plus x plus x squared over 2 factorial plus x cubed over 3 factorial. That's the expansion for E to the x. How many of you have seen this before? Okay, so not that many. We will see this later. These are called Taylor series. N factorial is n times n minus 1, 3 times 2 times 1, and 0 factorial equals 1. So n factorial is the number of ways to arrange n objects in order maps. And it turns out that no matter what x is, n factorial grows so rapidly that each of these terms is going to get smaller and smaller and smaller, and when you add them together, it's going to converge. Cosine of x, it turns out it's the same as 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus that. Sine of x is x minus x cubed over 3 factorial plus x to the 5 over 5 factorial. And amazingly, e to the ix is cosine x plus I sine of x, where either I is or I am the square root of -1. So we will spend a lot of time at the end of the semester looking at sums, infinite sums like this, and talking about when do they converge, and different tests for convergence. All of trigonometry can be deduced from this relationship here. And so at some point in the semester, I will talk about how you get all of trigonometry from this. Okay. So this is one type of limit. Another type of limit that you're more used to seeing is the limits as we approach a point. So for example, maybe I have some function like this. Here's a point x naught, here's L. We're talking about the limit as x approaches x naught of f of x equals f. And so this means as x gets closer and closer to x naught, the value of the function is getting closer and closer to f. You may have seen epsilon delta formulations of this. We're not going to really get that rigorous. We're going to just do standard way of view like this. It's important to remember that when we write x goes to x naught, it means x gets arbitrarily close to x naught, but it's never allowed to be x naught. If I change the value of my function and make my function this, it doesn't change the limit at x naught. What would you say though about a function that looks like this? It jumps up instantaneously, jumps back instantaneously, and continues. What kind of function would that be? Discontinuous. So if you don't equal your limit, you're discontinuous. So you're continuous at x naught if the limit as x goes to f naught of f of x equals f of x naught. So if the limit exists and equals the value of the function there, then we say the function is continuous. And we have lots of techniques to find limits. So we have rules like the limit of a sum is the sum of the limits, the limit of a product is the product of the limits, the limit of a quotient is the quotient of the limits, and all of these give rise to differentiation laws. Give rise to rules like the derivative of the sum is the sum of the derivatives. Now, the product rule and the quotient will become a little bit more involved, but they are coming from limit laws. it's extremely important to remember that when we talk about these, we want the limits to be finite. We saw the dangers of infinity minus infinity or infinity times 0. So if the limits are finite, then we're okay. If we have a quotient, that's the other thing we have to be careful about. If you want to say the limit of a quotient is the quotient of the limits, what do we have to be careful about? Good, that the denominator is not 0. And as long as the denominator is not 0, then we can say the limit of the quotient is the quotient of the limit. Okay, so we have lots of different ways to try to calculate limits. In one dimension, there's really not that many paths to go through. In one dimension, I basically move to the left or move to the right. So things become more interesting in several variables. The most important limit that you've seen so far is the definition of the derivative. So, x prime of x naught is the limit as n goes to 0 of f of x naught plus h minus x naught divided by h. This is excellent notation for calculus of one variable. Is the derivative related to the original function? You may even say it's derived from the original function, right? The name is a hint. So we want notation that basically says, hey, look at me. I am related to what you were doing before. I started with F, okay, I put a prime in the derivative. The problem is when we do several variables, well, which variable are we taking the derivative with? So this notation is not great. But this is the same right now as df as a point x naught. And this is the difference between the Leibniz notation and the Newton notation, or the fraction, or the dot notation. When we have several variables, this is the notation that's in line a lot better. It turns out there's more than one way to write the key limit in calculus. We could also write it as f on x naught is the limit as x goes to x naught of f of x minus f of x naught over x minus x naught. And to do this, really just take x equals x naught plus h. And so as x goes to x naught, that's the same as h goes to 0. These two are really equivalent. Turns out this isn't going to generalize well. What generalizes well is the following. The limit of x goes to x naught of f of x minus f of x naught minus f prime of x naught x minus x naught over x minus x naught. That's what's going to generalize nicely for calculus of several variables. So let's try to unwind what's going on. I like to always tell stories of speed. Okay, let's say you're traveling at 60 miles per second. Does your speed change that much over a short period of time? No. Exactly what is a short period of time that might be up to big? Is it 1/10 of a second, 1,000th of a second, 1 millionth of a second? But over a sufficiently small window, your speed is not changing that much. If you're traveling 60 miles per second, how far do you go in 1 second? 60 miles. How far do you go in 1/10 of a second? 6 miles. How far do you go in 1/100? 0.6. Okay. I'm more confident that there's no significant change in speed in 1/100 of a second than I am in 1 second. I'm even more confident at 1,000th of a second. So something to be discussed later is how far can we go? One of the key ideas in part 1 is I have a function and I have some point here, x naught, f of x naught. And the slope is f prime of x naught. So f prime of x naught is the instantaneous rate of change at the point x naught. And the idea is that we should be able to approximate our function by the tangent line. And the smaller we move from x naught, the better approximation it should be. So which equation of the line should we use for the information that you're given to write down the equation of the tangent? Which version do we want to use? What are we given? Point slope. So it would be y minus y naught, which is f of x naught, equals the slope f prime of x naught times x minus x naught. Or equivalently, y is f of x naught plus f prime of x naught x minus x naught. Have you seen that anywhere today? F of x naught plus f prime of x naught x minus x naught. Have we seen that anywhere? Where have we seen that? It's an numerator. So this is taking where I am and subtracting where I think I might be if my speed were constant. Now, how did we get this? We moved the f prime of x naught inside the limit. Does this have any x dependence? No. So if I take x, go to x naught, this is just a constant. I'm multiplying by 1, one of my favorite things to do. X minus x naught divided by x minus x naught. That's just multiplying by 1. So I'm just really subtracting the f prime of x naught. So another way of saying f prime of x naught is the derivative of f at x naught is the tangent line approximation at x naught is so good that even when you divide by this small little bit, it's small. Would you be impressed if I told you right now, just by looking at your eyes, I can see how well you are comprehending this and how well you will comprehend everything else for the rest of the semester, and I can give you your final average in class right now to within 50 points on a scale from 0 to 100. Are you impressed? Not particularly. Why not? Okay, so not only is it a really large scale, what else is it? The range from 0 to 100, I actually cover the entire interval. Am I giving you any useful information? What if I told you I could do this within a tenth of your final average? All right, well, that's pretty impressive. I don't have that. Yes, but this is the math. You didn't have math, for sure. But the math, I is not really nothing. To say the numerator is small, not a big deal. As x goes to x naught, what does x minus x naught go to? 0. And if the function is continuous, as x goes to x naught, f of x minus f of x naught goes to 0. The numerator goes to 0. So if I just look at the numerator, the numerator is going to 0. This is becoming a good approximation to the function. Well, yeah, because I'm not really moving on. But what if it is continuous? If it's not continuous, you can't even talk about differentiation. So the fact that the tangent line is converging to the function is not that big of a deal. But what this is saying is, even when you divide by the very small time unit, that's the right scale to study. Yeah. I have changed time by x minus x naught. And it's so small that even when I divide by that small amount, it goes to 0. Okay, now we're talking about a good approximation. And if you look at this, you can see it's a pretty good fit locally. But you're not seeing a big difference. Frequently, what will happen is this difference will be inside x minus x naught squared. And you can even quantify how quickly it's tending to 0. This is the notion that will generalize well. So what I want to do now is write down the definition of partial derivative. So for partial derivatives, we basically pretend all the other variables are constant. Only one variable is allowed to change at a time. And so if I want to do the partial derivative, you get df at the point x naught y naught is the limit as x goes to 0 of f of x naught plus h y naught minus f x naught y naught over h. And you can see that this notation is good. It's similar to the d by dx that we had before. It's slightly different, so it's reminding me, okay, it's not exactly what we had before. The variable that we're differentiating with respect to is playing a role. It's related to the function, has lots of things going on. And so now, we just calculate this limit like we would do in top 1. So if I give you, let's say, f of xy is 3x squared y to the 4th, and I want to take the derivative of this with respect to x. So what's the derivative of x squared with respect to x? Derivative of x squared, 2x. What's the derivative of constants times x squared with respect to x? If I had c times x squared, what would its derivative be? Just c times 2x. This is the constant rule. The derivative of a constant times the function is the constant times the derivative of the function. What we're doing here is we're pretending y is the constant. So this is really the same as take the derivative of 3y to the 4th times x squared. So it's going to be 3y to the 4th times 2x. Could we leave it like that? Sure. But it's nice to write it as 6x by the 4th. And that's how you would do a partial derivative. One of the difficulties is when you take partial derivatives, we are saying that there is a special direction or a special direction. The coordinate axes have now become special. And that's not good. Maybe the function is nice along the coordinate axis, but not nice along some other paths. And that could cause some real challenges later. So we will actually talk a little bit in this class about the theory behind when is a function differentiable. So have we already talked in this class about necessary versus sufficient? What is a necessary condition to win the Super Bowl? You have to play in the Super Bowl. Right? It is not a sufficient condition, however. Okay? So what is a necessary condition? What is a sufficient condition? The most important thing is you actually take derivatives to reduce stuff with it. But I want you to have a little bit of a sense of what are the challenges. Now, what if I gave you d by dx of 3x squared y squared plus y to the 4th? The derivative of a sum should be the sum of the derivative. And this is true so long as you have a finite sum. So this will then be the partial with respect to x of 3x y squared plus the partial with respect to x of y to the 4th. What is the derivative of 3x squared y squared with respect to x? What would the derivative of 3x squared y squared be with respect to x? 6x y squared. So y squared is just a constant, it's just 3y squared times the derivative of x squared. 3y squared times 2x, so it's just 6x y squared. What is the derivative of y to the 4th with respect to x? No. Zero. So this is one of the most common mistakes. Right? What's the derivative of 5 with respect to y? Zero. What's the derivative of 5 with respect to x? 0. What's the derivative of x with respect to x? 1. The derivative of y with respect to x, however, is 0 because that has no x dependence. So it's just 6xy squared plus 0. So when we are taking the derivative here, we are considering y as constant. You want to think of y as a number like pi or e to the pi, something strange like that that's not occurring anywhere else in the problem. And then at the end of the day, then we replace that back with y. Or you want to replace all the y's with a happy face. And then when you're done, remove the happy faces and put back the y. That's the mechanics of partial derivatives. Imagine I wanted to write a cool test to break your rule. And I have a choice. I can either do a cool test in derivatives or a cool test in integrals. Which would I choose? Integral. The big lie of Calc 2 is that you can integrate. You can't. If it makes you feel better, I can't integrate, no one can integrate. There are a couple of functions that happen to be really nice, and we can work with those. But most functions do not have closed form antiderivatives. But then why, when you take Calc 2, you have all these nice integrals? Because we work hard to give you functions that have nice integrals. But you should know that in general, it is hard to integrate. And later in the semester, we will actually talk about Monte Carlo integration, about what do you do when you can't do something in closed form. So for example, if I want the integral of e to the x squared, there is no nice closed form answer for that. However, what if I give you the integral cosine of x? What function is derivative cosine of x? Sine of x. Or one of these magic to get out of plus c over there. You say, hey, look, cosine has a nice integral. Okay, but what is sine of x? It's technically an infinite sum. There's a couple of values of sine and cosine that we can evaluate. The sine of pi over 4 is pi over 4 minus pi over 4 cubed over 3 plus 4 plus pi over 4 to the fifth over 5 plus 4, etc. Anybody ever read the comic strip box chart? So there's the youngest son is a huge geek and is hired by one of his siblings to help with trigonometry. And is asked to evaluate the sine of pi 4 or something like that. I think he does maybe pi third or pi fifth. And you have this infinite sum. And then the sibling says, I'm not paying you by the hour. And he goes, well, and when you look at that infinite sum, does that look like that should be root 2 over 2? If I replace pi over 4 with pi over 6, you would get 1/2. Just because I gave it a name does not mean I really understand it. We understand certain angles, and sometimes we can get other ones. So I am very big on notation. In the email that I will send, or probably already sent out today, there is a question on notation. I'm trying to see if you can identify something from a non-human representation. So when I wrote it like this, it's correct. But that may not be easy for me to work with. If I wanted to be cruel, could I give you a derivative that you can't do? If I give you a derivative involving sums, what do you do? What will you do? So your function is the sum of two functions. How would you find its derivative? Sorry? The sum of the derivatives. You would use the sum rule to hack it down and make it smaller. What if you had a product? What would you do? Product. What if I give you cosine of 3x squared to the x minus? How would you start taking the derivative? The chain rule. Whenever you hear of, you should be having a Pavlovian response. Whenever you hear of chain rule, whenever you see a product, you often want to think maybe a logarithm might be nice. I have to evaluate a product because logs and products are sum. Whenever I hear of, that's a chain. So if I wanted to do by chain rule, it would be cosine prime of 3x squared to the x sine of x. And then I have the derivative inside, 3x squared to the x sine of x with the derivative. Now what do I do? How do I do this? Product. And you might want to group two of them together, so it's product of two functions. And then you can use the standard product rule rather than the generalized. You keep hacking away. I cannot stump you on a derivative. I should easily stump you on a derivative. Okay. All right. Any questions on this? So what I want to do now is talk about some limits. And so we want to figure out how to calculate a limit. So in one variable, we've done that before, how we got to derivatives. The question is, can we come up with something more interesting in two variables? The answer is yes. So imagine I give you the function f of x y is xy over x squared plus y squared. So what is the interesting point for this function? We might have been interesting to find the limit. Origin. So let's look at a limit as xy goes to 0, 0 of xy over x squared plus y squared. Can anybody give me a nice path to try? Yeah, let's try the x-axis. So along the x-axis, this is y equals 0. We would have the limit as x goes to 0 of x times 0 over x squared plus 0 squared. Well, what is the quantity in parentheses? So x gets closer and closer to 0, but it's never 0. What does that quantity equal? What would it be? It would just be 0. Right? The numerator is 0. The numerator is not 0, so I don't have 0 to 0. What's the limit as x goes to 0, 0? 0. Now, if you look, this function is the same as f of yx. So keep the modes of x and y, it doesn't change the value. So anything I do along the x-axis, it's the same calculation along the y-axis. And so if I look along x equals 0, along x equals 0, we also get 0 as the limit. Anybody know the longest song to sing? Infinitely many bottles of beer on the wall, infinitely many bottles of beer. If you're over 21, what do you do? Take one down, pass it around. How many bottles of beer on the wall, Mary? Infinite. Infinitely many bottles of beer on the wall. The song never ends. How many casts are this to check? Infinitely many. How many have I checked? 2. We have a lot to go. So the more casts you check, the more confident that you should be, but it's not a proof. You have to check them all and show that every path gives the same limit, or find two paths that give a different limit. So if we find two paths that give a different limit, we won't get. No. So we can absolutely, but we have to do more work. So this will, checking just those two paths will only show the limit doesn't exist.
You just graph it.
And how do you graph it? How do you trust them?
Nice.
I had 1 year with 4 thesis students, and 2 of them had found bugs in that. You've got to be very careful. Can someone give me another path to check? X equals y. Or more generally, let's try y equals mx. If I put it at c parameter m, I can check all those lines simultaneously. And if I do that, I get the limit of x goes to 0 of mx squared over x squared plus m squared x squared. All right. What is the quantity in parentheses? You've got mx squared up top and x squared plus m squared x squared down below. What can we do? Can't let the x squared is the same as the limit of m over 1 plus m squared. And now we see that the answer depends on the slope of the line. Different slopes will give you different limits. It is possible for me to give you a function which has the same limit along all lines, but a different limit if you go to a, or to come out to a line. Not a plane. Your y equals x is a line with the next curve off the y equals x. X squared, a parabola. So I can give you something that has the same limit if you approach along any line, but a different limit if you come in along a parabola. I can give you something that has the same limit along lines and parabolas, but a different limit along a cube. So just because you're seeing the limits are the same doesn't mean it's always going to be. Now, when you look at this, you should see x squared plus y squared. As soon as you see an x squared plus y squared, what should you be thinking of? What's your Pavlovian reaction? Polar coordinates. So let's calculate the limit polar coordinates. So x is our cosine theta, y is our sine theta, x squared plus y squared is r squared. If we look at what's going on, we have the limit as xy goes to 0, 0 of f of xy, which is the same as the limit of r squared cosine theta sine theta over r squared. And now as xy goes to 0, 0, what must be true about r? What does r go to? So xy is going to 0, 0. What must be true about r? It goes to 0. R squared is x squared plus y squared. So if x and y are going to 0, so is the sum of their squares. Do we have any conditions on theta? No. As r goes to 0, the point r cosine theta, r sine theta is going to go to 0. Theta can do whatever the hell it wants. Theta is free. And so this is the same as the limit as r goes to 0, theta is free of cosine theta sine theta. Ah, that's not so bad. If theta is constant, then the limit exists, and it will be different values for different values of theta. So this will also prove that the limit doesn't exist. I could have theta vary. I could have theta equals 1 over r, in which case this is going to just spiral out of control. So switching to polar is often a great way to try to calculate some of these limits. Yeah. So if I take different values of theta, if I take theta equals pi over 4, then I will get root 2 over 2, root 2 over 2, I'll get 1. If I take theta equals pi over 3, and we get root 3 over 2, 1 over 2, I'll get root 3 over 4. And so if theta is fixed, the limits exist. I could also have maybe theta going into kind of range. I got range instead. And if I do something like that, the limit is not going to exist. It'll keep altering back and forth. The radius is getting smaller and smaller, which is good, but data is bouncing back and forth between maybe pi over 4 and pi over 3. So by choosing different thetas now, by choosing different paths of theta, I can see that the limit either be different values for different choices, or even doesn't exist. I think one last item for the day. Imagine I give you, and this will be a little bit different than the problem from the first section because I do not remember what it was. 3x to the 4 of 7x cubed minus 2x plus 1 over 4x to the 4 minus 8x plus 1. And I want to figure out what is this limit equal to. Well, let's look at the numerator. As x becomes very, very large, what is the numerator approximate a very large value of x? It's approximately 3x to the 4. When x is huge, if x is a quadrillion, this doesn't really matter. If I give you 3x to the 4th quadrillion dollars, you have. If I had a negative here, and said, oh, wait, I've got to take back 7 quadrillion cubed dollars. Fine. Not a big deal. The 3x to the 4th is going to dominate. So the way you handle limits like this is you pull out the highest power you can from the numerator and denominator. So from the numerator, I will pull out a 3x to the 4th, and I'll get 1 minus 7 over 3x minus 2 over 3x squared, 3x plus 1 over 3x to the 4th. And for the denominator, I pull out a 4x to the 4th, I'll get 1 minus 8 over 4x cubed plus 7 over 4x squared. And now I can cancel the x to the 4th. And when x becomes very, very large, I want to say the limit of a quotient is the quotient of the limit. What does the numerator go to now if x goes to 10? Just the numerator. Oh, good. Yeah, this part here is just going to go to 1, so the numerator just goes to 3. The denominator simply just goes to 4 because if x gets very, very large, this part over here is 1. The whole point is I'm avoiding having 0 over 0 and 10 over 10. I can just say the limit of a quotient is the quotient of the limit because it blows up. So I just have to pause for a moment. I pull out the highest power, and so here I would just get to the 4. If the numerator had a higher degree of x in the denominator, it goes up to plus infinity. If the numerator has a lower degree, then it goes to 0. Right, so this is a good place to stop for the day. We've done a lot of good stuff on limits. Now I'm just trying to do is I'm actually trying to just see. I just want to save the transcript before I stop it.